So welcome to Demography Today lecture series, sponsored by the BBVA Foundation and co-organized with the European project Horizon 2020 LOMPOP project on longitudinal registers and big data. And because we are very interested in big data, we thought that the best thing to do is just to call one of the main enterprises in Europe and in the world on mobile connections and telephone in general, and on big data, which is Telefónica. And we asked Telefónica I+D and Enrique Frías specifically to come here to talk with us and to present some of the work that Telefónica is doing on big data. So thank you very much for coming here. We are very lucky because Enrique has been working quite a lot, extensively on the analysis of big data. We will see very nice examples of this work. Enrique has been is working in Telefónica research and development. He has been already for 10 years working on big data. He has been at the Department of Biomedical Engineering at the University of California, UCLA, and then as well at Brunel University in London and the Courant Institute of Mathematical Science in New York University. He has been writing extensively about big data and doing quite nice presentations. So thank you very much, Enrique, for coming here to share your knowledge with us. And I hope that we will find ways to collaborate in the future between demographers, epidemiologists, public administration, and private companies like Telefónica. So thank you very much.
Thank you. So when you contacted me, you wanted me to present especially a work we did maybe like 3 years ago or 4 years ago in studying H1N1 using cell phone records. So within that umbrella, what I would like to present is what has been called big data for social good, or how can we use this data that we are generating, this data that we are gathering, and how can we extract insights for social applications. And I'm going to focus in two main areas. One is epidemics and depending on the amount of time that we have in migrations. So obviously I'm going to talk about cell phones, so let's start by cell phones, right? So basically, nowadays we can assume that everybody in the world has a cell phone. Actually, these statistics I'm presenting here are like 2 years old. Sometimes we have more cell phones than population. We have countries that reach 120%. That was the case of Spain, like around circa 2008, 2009, before the crisis. Then we went down to like 90%, and we're going up to 100%. And this level of penetrations can be applied both to developing and developed economies. Actually, in developing economies, your cell phone is way more important than in our case. Things like banking happen just through your cell phone. Things like if you live in a rural area, things like the price of the things that you need for your farm depend on your cell phone. So cell phones in developing economy are very, very important, which derives that the concept of big data for social good using cell phones can be very easily implemented in developing economies. And we can derive all these insights using cell phones because basically we spend more time with our phones than watching TV or with our partner. That was a study done like 3 years ago, so I'm particularly in the States, which is quite amazing. I don't think we realize the amount of time that, not that just we carry the device with ourselves, but the amount of time that we interact with the device. And this thing is going to be more and more. Right now it's in the States. I would be surprised if this also does not apply to Spain. Okay, so cell phones, as a result of all this, cell phones have become the main sensor of human behavior and human activity. There's no technology in the history of humanity that has been so tied to an individual. And as such, we are gathering a huge amount of information of each one of the individuals that carry those cell phones. No? This, for me, as I see it, is an unprecedented moment never have we been generating and gathering so much information. I'm not just talking about cell phones, but there are like thousands of devices that also generate this information. And this opens an opportunity to study what we can obtain and the insights that we can derive from these cell phones, and also have a lot of problems of, okay, so how we capture this information, how we store this information, how we process this information, how we adapt the algorithms that we have known up to now to this new scale of data that we have. So this concept of big data for social good, actually, although it started a little bit like an evolution that nobody really was claiming of big data, eventually reached the United Nations, which I think it was the first case that a global institution actually highlighted the importance of what can be the impact of big data for social good. And what the United Nations is now trying to push is a data revolution. So these things here is that the Sustainable Development Goals of the United Nations, and in all of them, the United Nations is pushing an approach towards using data. Some of the examples I'm going to present here. All of the examples I'm going to present here can be categorized in one of those, right? Like, for example, there's a specific for health, or there's specific for climate change. And because of that, the United Nations created what they call the United Nations Global Pulse. The United Nations Global Pulse is a unit within the United Nations that depends directly from the Secretary General, whose goal is one, collect data from countries, and for that they open labs in specific countries, and two, collaborate with companies like us, for example, like to combine these data sets they're generating to generate knowledge with social impact. So this slide here is in no way like a global thing. I just wanted to present the main players right now in big data for social goods, right? So we have like this part here, which will be like companies that already have this data. It will be like telco companies. Orange is working quite a lot in big data for social good. Telefónica is. BBVA Data Analytics actually has a lot of examples of big data for social good, also working with the United Nations. Things like Nielsen, Bloomberg LLC are companies that have this data that they are generating for other purposes, but they collected this data and are pushing the use of this data for this kind of applications. Then we have like these international institutions here over here. Obviously we'll have here governments or national statistical institutes. And all of them are creating or already have big data application for social good. The main one being United Nations for Social Good. UNICEF has its own data analysis unit for social good. The World Bank and Inter-American Development Bank, both institutions, we have collaborated with them. They are very interested in trying to gather how to study the economic development of a country with this kind of data, or how like natural disasters affect them and how they can recover the previous economic development and so on. And on the third case, it is on the top, and I don't know why you cannot see the other ones, but anyway, they're like startups that are starting, like Flowminder is one of them, Datapop Alliance is another one of these startups that within this sense of we have data, we have these institutions directly of the data, are trying to give these services. Flowminder will be like, I think one of the main ones, for example, here these guys study, the first big data for social good study was the Haiti earthquake. These guys took the CDR data and studied how people moved in order to give that information to emergency agencies so they can deliver help and food. Again, this is in no way like exhaustive search, just the main players, right? So let's go now, and I want to give Lily some details about the data that we use for gathering or collecting or generating insights. So how does a mobile network work? So a mobile network, we have these antennas, which are, you can see them all over the place, which they have different panels. Usually they have 3 panels. Each panel covers like 120 degrees. So you have these cells, which are called an area of coverage of an antenna, which is the area that this antenna gives service. So if you're in that area of that antenna, your cell phone is connected to that antenna. This is done actually completely automatically. If you, actually 20 years ago when we have analogic cell phones, you have to do that manually, which was quite funny. The size of these areas depends on, basically there's a strong correlation obviously between the density of cell towers and the density of population. You want more towers, you have more population, although there are cases like soccer stadiums are good examples that have a huge number of antennas that is only actually used in very specific moments. But in general, there's a correlation between density of population and density of towers. So in this thing here, what you see is what Spain is divided in. This is the area of coverage of Spain, of the towers, and this is the information we're collecting, right? So you can easily see cities. Okay, no. So you can see here, obviously Madrid or Sevilla here. You can easily see the high speed. For the high-speed train was a specific infrastructure developed. You can see here, for example, the Madrid-Sevilla connection. The same thing with the AVE that goes north. And these areas over here, they are pretty big. I mean, you're talking about towns that maybe would give service to 10,000 people, but you can collect information about those people. And some statistics, there are 150 antennas, 21 million of Movistar clients use this infrastructure, and about close to 1 million roamers a day. This is basically tourists. And this is a very nice insight about how being tourism one of the main industries of Spain, what can we gather? And so this is how we collect information. This is the granularity of the information that we collect. And remember this map because later when I compare it, for example, to Mexico, for example, to Colombia, that the distribution of population is not heterogeneous at all. It's a very different map in developing economies, and that has an impact in the studies that we can do. And if we granular level, this is the, actually I want to show this building, but I think this is north from here. No, a ver? See, this is not from here. So this is downtown Madrid. So you get an idea of where can we collect. So if you are here, you're probably working. If you're repeatedly here, you're probably working. This is like a government office. If you are here, this is a very nice residential area. If you're up there, you're a soccer fan. If you live there in that corner, that's another residential area, not as affluent as this one. So you know which people, how they behave. And it's by this, like knowing this, where people goes, that you can characterize this mobility of people. You can see how they move to one area from one area to another. And you can assign the semantics of what happens if they are there. And an important thing is that we are simplifying it. See? So for example, this tower here that gives coverage to the Museum of, this is the Museum of Natural History. These straight lines are obviously an approximation. The real coverage is way much more complex. Antennas overlap among them. So this visualization I'm presenting here is a simplification of the actual coverage that a tower gives. And I want to give you some detail of the actual data that we deal with. So this is, when you make or receive a phone call, this is the data that is being generated. So it's called a CDR. It's a call detail record. This call detail record has an origin phone and a destination phone, which are encrypted or are hashed in a table, so you don't see that phone number. You have the time when that interaction happened. You have what is called geo. You have a indication of the towers being used for that communication, so you know where the cell phones were located when that interaction happened. And then the date and the time and the duration of the call, if you're interacting, how long did it take, and then a lot of like codes regarding if there were errors or things like that. Something very similar when you send an SMS. Nobody sends SMS anymore, right? We're losing that source of information. But anyway, the information is very, very similar. This is a very important thing to keep in mind. When working with telco data, you have two main sources. One is CDRs. CDRs, you only have the information, there's an interaction. If A calls B, there's a record there. If you're not calling anybody, we don't know where you are. If you don't use your cell phone, you make or receive calls, there's no information there. If you go at a deeper level, what is called network traffic level, then it's a passive information. That's even more powerful. Not that you need that for information because it scales tenfold, but the network in every moment, if we go back here, the network environment needs to know where you're located. In case somebody calls you, they need to reroute the call, right? So in that case, there's a passive information that is being generated that you're not aware of that. And the network knows where you're located because they need to pass you the call. And depends on how the network, in the UK, for example, every 2 hours, the O2 network pings some cell phone and gives the location. In Spain, it's 3 hours. That depends on how the network is defined and the quality and so on. That passive amount of information, it's much more powerful, generates much more information, and also presents new challenges, right? You need the storage and the processing is very different. But in general, with CDRs is a very powerful source of information, and we can do a lot of studies with them. And what can we derive from this CDR, of the combination of CDR and SMS? Things that are interesting from a company perspective, which are obvious that we are interested in, like the number of calls. If you tend to do calls one after the other, or just one and then 2 days later another one. If you have a reciprocal calls, how much time are your calls, and so on. Social networks. Well, social network was like one of the main things that telcos companies started. Now we're losing the social network. Nobody calls anybody else. Everybody goes through WhatsApp. So usually you will call somebody that is not actually close to you. So the value of social network from a telco perspective is going down, just because it's not the main source of communication right now, right? But potentially you can obtain the in degree and out degree, how many people you call, how many people calls you. You can obtain the unique calls that you get, the reciprocal calls that you get if you're an important user, if you're the influence that you have over other users. And which is more important, I think, for this presentation is the mobility. So you can see, you can identify where somebody lives at a tower level. You can identify where somebody works, or assume that that's where they work. You can identify the distance that they travel one day, that they commute. You can obtain something called the radius of gyration, which is basically assigning the number of calls to each tower. So you obtain basically a circumference, which is the area of the city that that person covers, and the radius characterizes that area, and so on. And with all this information here, this is some insight that we obtain, that then we aggregate, and then we apply to some of the applications that I'm going to introduce now. Okay, so this is the main areas where institutions and policymakers are interested, right? We started with urban planning. That was actually how I reached social good. A lot of information on how people move at a level that is very difficult to capture, or where does people go south, and so on. And crisis management tools, which I'm going to present, and public health tools, which I'm also going to present. And obviously, I'm going to focus on call detail records, but I want you to keep really a broad mind of the data set, just because the examples I'm going to present are focused using, or are based on CDRs, but any geolocation information can be used. So when thinking about data mining, big data for social good and the data sources, there are a myriad of data sources. I mean, obviously phones is one of them, but all the apps are surrounding that phones are very important. Twitter, Facebook, Foursquare, you can actually download that data and make studies with that data. All the public transport system generates a lot of information. We have bike systems that, for example, we did with Barcelona, that you can study how the bicycle system works, where they have problems of unbalanced stations. Bikes tends to be in one place, in one other. That's also a visualization of the city. Smart metering, which is already here, and everything related to cards. BBVA knows this very well and is using this very well, and they provide a lot of information of individuals and also some mobility, right? Okay, so let's start with the application of CDRs to model the H1N1 pandemic that happened in Mexico in 2009. So what we wanted to do here was actually a tool. Mexican government was involved in this, and basically, they told the population, following what the World Health Organization told them, you're supposed to stay at home, you're not supposed to travel, and so on. They wanted to measure to which extent people actually follow those directions. They actually stayed home, they actually reduced their travel, and so on. So we created these studies, these tools that try to measure that. This was what happened during the H1N1. So we have a pre-flu situation where no alarm was raised. On April 17th, we have a medical alert, which was one kid in some rural area that was tested positive for H1N1. April 27th, all schools and universities were closed. From May 1st, all non-essential buildings were closed. When the May 6th, everything reopened and in theory went back to normal. The goal here is to reduce the mobility of the population, to tell people to stay home, so you reduce the contact with people that can pass the virus on to another, right? Also, we have to consider that there's a calendar here. When evaluating, you will see later when evaluating what really happened, May 1st is already a holiday. In Mexico, May 5th is the Cinco de Mayo, it's already a holiday. This was a weekend, so you will see that this was as impactful than you would expect, basically because a lot of these dates were already a holiday. Okay, so the two main questions I wanted to answer here. So can we measure the effect that government alerts had on the mobility of the population? So the Mexican government, following the World Health Organization, told people to stay home according to the previous calendar. What was the effect of that on the population, or also on the mobility of the population? Can we measure that, give a number of the reduction of mobility? And also, can we measure the effect of that reduction of mobility on the spread of the virus? So basically, we can give an estimate of the percentage of less people that was infected of the virus because of those actions. Okay, so epidemic disease models are by themselves a huge research area, obviously, that has been going on for many years and that with traditional models has worked very satisfactorily, right? So the traditional models are called the compartmental models, which you have the population divided in compartments, which are isolated one from each other. The typical model is the SIR model, so you go from susceptible, that means that you can become ill, to infectious, that means that you have the virus and you're passing the virus to somebody else, to recovered, that means that you have developed, you have been vaccinated, or you have cured from the virus, or you are dead. Because here we wanted to model H1N1, these compartmental models, and there are a variety, we consider the SEIR model, which is includes an exposed situation, an exposed state, which means that you have the virus, but you cannot pass the virus on to somebody else. So this model here, you have this contact rate, the transmission rate, and the recovery rate. These are formulas that express the probability of a group of population going from one state to the other. So these compartmental models do not capture the individuality that we have. I mean, they put everybody there. And it has to be said, they work very well. And this has been the basic tool until 5 years. And they work very well, and that's how they are made plans. But they have their limitations. They don't capture individual mobility. They don't capture the particularity of individuals. Everybody there is the same. And the models that we obtain are for a country level. That's why you see H1N1 and you see these graphs of how it spreads at a global level. That's because these models work at a global level. If you want to do that at a city, this is very difficult to implement. In order to solve this situation, there was this new approach that started like 5 years ago, which is agent-based models. Agent-based models is something of software engineering, where an agent is basically a piece of software that behaves as something else. You can have an agent that behaves as an animal, an agent that behaves as a person or as a car or whatever. You just put some rules that within a scenario tell them you have to go to work now, you have to come back. If you like video games, that basically any character of a video game, it's an agent. And you tell that agent how they're supposed to behave. Okay, so agent-based models kind of solve the approach, the problems of that you are not able to capture the individuality of each person with the traditional models, right? So you can create an agent, which is a piece of software that you say, okay, this person represents a male in their 40s that lives in downtown Madrid and that has a job here and there, and you create that behavior there. It still has some problems on the traditional approach. That is, you have to, in order to create this model, you have to fit the model information. And that information, if you, up to when we did this, was basically using National Statistical Institute aggregated information. So what's the average distance that somebody travels to work in Madrid? 15 kilometers, so you're creating an edge of that. So although they kind of solved the problems that we have with the compartmental models, they are limited by the availability of information. You want a good agent-based models, you need to provide the agent model with good information to simulate the human behavior. Okay, so what we did, let me go back. What we did was okay, let's do an agent-based model system because we want to capture the individuality of human behavior that will have a model that explains the evolution of H1N1. But instead of using traditional sources of information that are collected from national statistical institutes, we'll create the models with information collected from CDRs. In that case, one model can be one person. Okay, so each one of the models of the pieces of software were given three models, right? A mobility model, you tell the agent how we're supposed to move. And social network model, you tell the agent with whom he interacts. And the third one, which is the disease model, I will explain later, which will tell how does the disease affects the agent. So the mobility model was obtained from cold detail records, was a statistical model that we divided, that basically tries to express the probability of a person of being in a given tower at a given moment in time. You have the information of CDRs, you collect that information. I say, so Monday at 12, the probability, the most probable for this person is to be in this tower. So you have an actual position of how that people moves. We created different models for mobility during weekdays and during weekends because it's well known, and we have found that it's very different, your mobility in weekends than in weekends, and that has a lot of impact in the model. Okay. So then, now that we have this agent that knows how to move in our area of simulation, we'll create a social network, which we tell them with whom he interacts, or again, from the CDRs. So we collected information with whom he interacts, which is the people which he calls. And the assumption, what we wanted to capture here is that, okay, if you are connected to the same antenna with somebody that it is in your social network, the probability that you're physically close is really high compared to persons that are not in your social network. So, and that has a very strong impact for like H1N1, which was a person-to-person virus, right? You need to close physical contact. And the third model that each one of the agents contained was a disease model, which is the SEIR model, which you go from susceptible to exposed to infective to removed. And these are the equations that evolve from one state to the other. So you go from susceptible to exposed. That formula there that basically expresses that the probability from going to your susceptible to be that you have been exposed to the virus increases with the number of people that you are surrounded that have the virus and the longer you are surrounded by that people. And to go from exposed to infected and from infected to removed, there's an amount of time. These variables here that the disease model has are actually obtained from the actual illness. So when the first cases are detected, you know, if you're a doctor, you study that. So, and these are measured in hours, and the more cases you have, you obtain a measure for that. For that, you need some previous study of previous cases or actual cases that give you how this beta or epsilon, what's the value in hours of those values, and that has to be measured inside. Okay, so what we have now is we have created these agents that have a mobility model, a social network model, a disease model. We'll see now this particular case how many agents are there, but each one have these models. And then we run them through a discrete event simulator. This is something that's basically an architecture that moves the agents around. So the first step of the event simulator is, okay, so you start the simulation at T0 time and run from whatever you want. We run it for 1 month. You start at T0 time and say, okay, where's everybody at T0? You run the mobility model and tell you, so agent 1 is in this tower, agent 2 is in this tower, agent 3 is in this tower, and so on. Each one of the agents are located in a tower. Then once you have, for each tower, the agents that are in that tower, you see, okay, for each one of the towers, which one is my social network? So you assume that the person that is in that tower with this social network is physically close. And once you have done that, you apply the disease model. So for each one of the interactions, you apply the probability. Obviously, you need to fit the system. At the beginning of this discrete event simulation, there's an agent that has the virus. And in the simulation that we ran, we simulated somebody landing in the airport that has the virus and run the system. That is T0, somebody landing in an airport with the virus. And from that, we evolved the simulation. Okay, so what was the real case of H1N1? So we collected the collated record from January 1st to May 31st. This covers the pre-flu situation, and this covers all the different stages of the flu. And with that CDR information, we created what are called scenarios. So we created a baseline scenario. The baseline scenario is like, okay, let's assume nobody did anything. The government didn't do anything. What would happen in that case? And then they assume the scenario of the intervention scenario. What did the government did? Stay home, total closure of activities, and so on and so forth. And then this scenario approaches is very useful for H1N1 or for anything, right? You want to see the impact of a change. You have to create a scenario, a baseline scenario, and then you have to run the simulations to measure what has changed against this baseline scenario. And obviously, as I was saying, each one of the agents has a mobility and the disease transmission and the spatio-temporal evolution. So for the case of H1N1, we run the simulation with a granularity of 1 hour. So the mobility models will express in which tower you're located per hour. This is very important. We required that each person had at least 20% of the slots filled, meaning that you have 24 hours. You need at least to have a call in 20% of these slots, and one call every 4 hours. There's a study there that was published in Nature that this is basically the requirements that you need to have to be able with a 90% of accuracy to pinpoint the location of a person. Now, this filter here, because basically you're only, for your simulation, you will only consider persons that pass these filters, obviously has a bias. In the case of Mexico, my impression was higher socioeconomic status. In a country like developing economies, really people use the cell phone not quite a lot, right? But anyway, you also have a bias here. So after applying this filter, and we selected not the whole country, we focused in one city, which is Guadalajara, Mexico. Which was Guadalajara in Mexico, not Spanish Guadalajara. We considered 25,000 agents. That were the number of individuals that passed this filter here. So of those persons, we were very sure that we were able to pinpoint very accurately their location. And we created the agents for each one of these phones with their mobility model and their social network model and the H1N1 model, which had this reproduction number, latent period, as we discussed, that were provided by the literature, right? And this a little bit of a repetition of what I've been explaining, so I don't think we need to go over this. Okay, so this is one of the big results. So this here measures the impact of immobility that the calls of the government, of the Mexican government, had on the population. So let me explain. The red lines expresses the baseline. So what would have happened if the government didn't do anything? And for that, what we did is we ran the simulation, the discrete event simulation, with the mobility models created with a pre-flu situation. So before March 17th, when the first flu case was detected, we assumed that the behavior of the population was the same after that first case. And that was the baseline scenario. And what we measure here is the percentage of agents that change a cell. So they move. It's something very simple. You're in the cell, you go to 3 cells over there, that's one change. So basically you're moving. So you can see very well, so each one of these peaks basically is a day, right? So you can see very simple, this will be Monday, Tuesday, Wednesday, Thursday, Friday, and weekend, Saturday, Sunday. Weekend mobility is reduced and so on. So the red is the baseline. And these things here are the periods. So this is the pre-flu situation. This is the alert when the schools were closed. This is suspension of non-essential activities, and this is when things were reopened. And the blue is when we're trying to simulate what actually happened. So here we run the discrete event simulator with the mobility of the phones during the actual mobility during the alert, during the close, during the suspension phases. And you can see the difference in mobility. Again, this is a very basic mobility, right? It's just change of tower. You go from this tower to that tower. We don't care about which tower, we don't care about anything. But you can see how just basically compared the alert period when nothing was really closed. There was one case and before everything was closed. If you compare the blue line and the red line, there's a 10% by this metric of change of towers that was reduced. And it's very close that basically weekdays from Monday through Friday in the blue line are basically behavior like weekends would be in the baseline scenario. Now during the closing of schools, which is this thing here, you can see that the 4 days that the schools and universities were closed, basically the reduction in mobility is over 20%, and you behave like a weekend, that the suspension of non-essential activities, that the mobility was drastically reduced. This is the blue line, and again, when you go back to reopen, people started moving basically the same. The blue line and the red line are very close. Sorry, so the answer here to the Mexican government is yes, people actually followed your recommendations, they stayed home. 10% they moved at this metric of movement, 10% less during the alert, 20% less during the closing period, and even peaks during suspension of 30% less movement. Okay, so that was good. And then let's say, okay, can we see this as at an infrastructure level? What was the impact of this change of mobility in infrastructure? So we took the airport, and we took one university. This airport and university have a type of coverage. See, the airport has only one tower that gives coverage to the airport. The university had 2 cells that give coverage to the campus. I wanted to measure how many people, what was the change of people that went to these infrastructures during the enactment of reduction of mobility. Basically, it's counting people that appears there, right? It's more complex than that because you have here urban areas that there's people that live there that you need to filter. You have people that work in the airport that you need to filter, but in the end, it's counting people and just counting the correct amount of people. Okay, so this is the university campus. And again, you have a baseline, which is the average of these 4 days and what really happened. So on average, the Monday through Thursday that were all schools supposed to be closed, the baseline is this one here, and the stage 2 alert, you can see that there's actually a reduction of the people that visited the campus. So not that much, but there was a reduction. Now, the interesting result here was, for example, the airport. So the airport. The red line is the baseline. So on a given Monday through Thursday, the average number of people that visit that airport that do not work in the airport, go to the airport to visit. The blue line is the actual number of people that were in the airport during just before the closing of all non-essential activities was implemented. So here Friday was May 1st, everything was supposed to be closed. And we see here that before this total closure of activities was implemented, there was an increase in the number of people that visit the airport, somewhat defeating the purpose of the whole thing. You want people to stay home. What people did here is just before everything was closed, they went to the airport, they basically went home, had a vacation, whatever, and they traveled just because they couldn't travel. There was while there was a reduction of mobility for specific infrastructures, like in this case the airport, you see that more people went to the airport, and just before everything was closed, they actually went somewhere else. And that had an impact in how the virus spread because it was not contained, right? So in the future, what should happen, you need to teach people that closing of non-essential infrastructures doesn't mean that you need to travel before those things close, because you defeat yourself. You just travel before you're supposed to travel. That was the case here. We also studied a hospital, for example. Some people went to a hospital. In a hospital, there was no change. So what was the effect on the epidemic spread? So this is the tip. So we run the simulation, right? And the blue line is the baseline. It is the number of agents that were infected by H1N1, and this is the days that we run the simulation. So this is the blue line. The peak of the H1N1 was around like May 2nd. And this is the percentage of agents that were infected in the area of 24%. Now, we compare this to the literature and our agent-based system. The curve was basically the same. In one case, you get 30%, in other cases, you get 22%, what was in the range of what the literature had published. And this thing here over here, the green line was the intervention scenario. What happened because the government told people to stay home. So as a result of that, we found that the peak of the epidemic was postponed like 40 hours, or almost 2 days. This is very important because if you want to enact people being vaccinated, people being evacuated, or do something, gives you 2 extra days to do something. And there was a reduction in number of HH infected. This number is wrong, in the area of 5%. Now, what we have done up to here, kind of there you can find the literature, right? And the power of what we did here was that we could measure what we did against as a baseline scenario. So because you did that, you know, is it worth or not worth taking these World Health Organization guidelines for avoiding the spread of the virus? That's the extent of the impact. For me, what was important, or what was really relevant here, is that, and that was not possible up to this study, we can run simulations at an urban city level. This is the city of Guadalajara, Jalisco, and you can just count the number of agents that were infected in each one of the areas. So you can prepare a plan not at a global level, for a country level. You can prepare plans for a city level, which I think can be very impactful, right? We had a case in Madrid of Ebola, of one person with Ebola. That's an ideal situation of applying something like a simulation, what would happen if that something gets infected, right? And nobody can achieve this level of granularity in the simulation just because that information is not available. So you can see here what was the situation in March 8th. It's one of the cells, the number of agents infected. There's nobody infected because that's when the simulation started. We simulated that, again, somebody landed in the airport that was infected, and then you run the simulation. This is the number per area of infected agents in April 19th. This is the peak, May 3rd. You can see the area of the city that has more people infected, which was downtown here. You have here the map of the city. You see the metro, which affects how actually the virus spread, we found out. And obviously the area with more infected individuals is here in downtown, as you would expect. But you can pinpoint the areas that have, and then May 14th, the epidemic is already going down with some exception areas. This is the power of an agent-based system using cold data records. The level of granularity that you achieve as compared with using National Statistics Institute is not something that can be done with that. Okay, so funny enough, here we didn't see a difference between the baseline scenario and the intervention scenario. From a spatio-temporal perspective, they both spread the same thing. Actually, we stopped here the research. I'm sure there are metrics to measure that, but there was not really a big difference on how the virus spread in one scenario or the other. So just let me say that we are applying now this same concept to dengue and Zika spreading in Colombia. Both of these cases are trickier, right? Because you have a mosquito, which is the vector of transmission, but a mosquito can be an agent too. A mosquito is in a specific place and depends on the temperature and humidity. And it's a little bit trickier, the system, because you take agents that are persons, agents that are mosquitoes, and they can interact between themselves and so on. You need some extra information. We're working here in this with the United Nations Global Pools, that they provide information of, because they have labs on site of where it's water located, where they have found where they have found mosquitoes, nests, the humidity that affects mosquitoes, wind, and things like that. And let's see what results come of that. Okay, so I think I have like 20 more minutes. And I just want to present, not at a, let's say, higher level, other applications of using cold data records, in this case more being for migrations. Okay. It's very easy with cold data records to see change in population when there's an earthquake, when there's flooding, there's a lot of people moving at a very specific moment of time that you need what to look for. It's more difficult to see what, when there's climate change, you see droughts, for example, rising level of waters. That's a more thing that happens over time. It's more difficult to capture. Here, what we want to capture, this is also a work with United Nations, if we can use cold data records to actually measure the number of people that migrate due to, in this particular case, was droughts that happens in La Guajira. La Guajira is a region in Colombia, that region over there that borders with Venezuela, that by itself already has droughts and very drastic droughts. But starting in 2014, these are the 2 droughts that have been going on for quite a long time. There's not only the problem of droughts, if they depend on the food supply coming from Venezuela, which they close the border, which affect the people that is there. There seems to be a lot of corruption. They want to build all these dams and infrastructure to deploy water, but there's a lot of corruption and things get stuck there. So they basically have been going on with a drought situation, and actually people dying and animals dying for quite a long time, over 2 years now. That actually caught a lot of the attention a couple of years ago. So you have up there what is La Guajira, and within La Guajira you have the town of Uribia, which is up here. And the town of Uribia actually in in February 14th declared the state of emergency. And as far as I know, still in that state of emergency. And we wanted to see if we want to measure the number of people that left La Guajira in general, Uribia in particular, due to this drought. And we have to be careful here. Assuming causality is very strong, right? You're measuring something, a descent, an increase or decrease in population, that it's correlated with a drought. So the drought is there and the temperatures go down. So I wouldn't go as far as claiming causality, that we are measuring that this drought causes, I'm measuring here this decrease in population. Obviously it's a part of bigger, right? Of something bigger. But what I am showing now, we definitely detect those trends. So the question here is, can we measure the effect of the drought in the population of La Guajira using cold data records? And then can we model this climate-based migration? So we had for these 6 months of data. Basically, this is the dry season, and it lasts until February, and then February through May is actually when the drought was, the state of emergency was declared in the town of Uribia. Remember I told you the map of Spain. Here you see a big difference, right? This is quite big, La Guajira. This all the towers that you have. So the granularity that you have is somehow restricted by the towers that you have, but this is because the density of population is there. I mean, there's no tower, there's no population. I mean, there can be population, but not enough for a tower, right? And you see, for a city perspective, the town like Uribia has 1 tower that gives coverage to the whole town. This is Rio Hacha, which is here, has more towers. In this case, like 6, 7. But anyway, my point here is just that this is the very typical undeveloped economies. You have towers in cities, towers in roads, and that's it. The rest is basically empty. This is very different, for example, the map from Spain, the map of coverage from Spain, the map of coverage of towers of the United Kingdom is very different because things tend to be more homogeneous. And that has some impact in what we did, which this is in our case plays in our favor because it's very easy to identify somebody moving because there are not a lot of number of towers, but for other studies can have an impact, right? So what we did here is apply what is called a home detection algorithm. A home detection algorithm is an algorithm that, based on your behavior with your phone, assigns a tower. We're not interested in your address or where you live. It's a tower. It's an area of like half square kilometer. Just by the repetition of your calls, we can identify where you live. And the algorithms applied here can be more complex or very simple, something like, so where your calls made or received, 7 p.m. to 7 a.m. The tower that you use over a period of 1 month, that's the tower, that's your home tower. by assigning home towers to the people that live in La Guajira and how these people move, we can measure what was their home tower per week. So we did this study for the town of Uribia. I keep confusing. So the town is Uribia and La Guajira is the province, right? So this graph here that you have here, this is for Uribia, and this is for La Guajira. And you have here the number of people that have home in Uribia and that have home in La Guajira during the 7-month period we consider. And you can see the trend going down, and the R-score is very good. So there was actually a 10% of people that migrated from Uribia and 50% in La Guajira, which is the province. It's expected, you know, if you work at a smaller scale as Uribia, you have more jumps, while working at a whole, let's say, state level as La Guajira, the graph is nicer, it's something more smoother, just because you're dealing with more information. So yes, there's a migration. You can measure that in the migration cost to the drug is in the area of 10% to 15%. You can also see where people migrate. So, and they're out of models of migration here, right? And we try to model that later. The red corner there is La Guajira. So most people that migrate stay in La Guajira. They just go to urban areas where they have better water deployment services, or they go to closer neighborhoods, and with the exception of Bogota. This is explained basically by the gravity model, right? The people go to big centers or places that are close. And basically, for this particular case, they, to some extent, follow this kind of migration, this model of migration. We wanted to study it, right? This kind of mobility, this kind of climate change migration, which kind of mobility model can be considered. So we tested gravity laws and we tested radiation laws and some variation of those. And what we found out that the best model is like, so the blue line is the radiation model, which is, actually is the blue model is the radiation extended model, which works very well, for example, to explain commuting. It's a model that explains that you will go to places where you can find a job, which kind of applies to us actually in the area of 60%. And if you go not to predict the number of people, but to predict where people migrate, in this case is not as good. But anyway, we have this behavior that can be somewhat explained by the radiation model that we can improve that. There is no model there with the particularities of a climate change migration model, right? Okay, so these are kind of the conclusions. Again, the models, the extended radiation model explains only 60% of the movement. So and we're working on that, trying to create a model, and maybe we gather temperature that we can better explain this mobility. And okay, I will finish with this one. This was an effort, quite a big effort, between, again, United Nations Global Pools that wanted to use this kind of approach, Telefónica that provided the data and the analytical power, the Universidad Politécnica Madrid that has a center for this kind of studies, the World Food Program that is very interested in this kind of studies because after a crisis they don't know where population is. They need to have information on site to deploy food basically, and by the Presidencia, so the Mexican government. So what happened here is, okay, and there are areas in the Caribbean that are repeatedly being flooded. That has an impact, you know, population has to be evacuated. That has an impact on the economy, especially economy based in tourism like the Caribbean and so on. So we wanted to measure the effects on the Tabasco floods. So Tabasco is this region over here. It's close to the Yucatan Peninsula, almost there, but not there, is here. And has a lot of floodings. And so we wanted to measure the mobility of the population during those floodings using a combination of data sets. NASA has this huge data set of satellite capture images of weather, and obviously with census data and with the information provided by Telefónica to see. First, we use this data to identify the areas that were flooded, use this data against CDRs to check to which extent CDRs were actually capturing the variability of the population, and then CDRs to measure the mobility. Okay, so this was something that is very interesting. Actually, first thing you do, okay, so if you have the CDRs of one company that you only have a partial view of the population, is that enough to characterize the whole population? These kinds of tries to answer that, so in a very particular way. So for that, use information on the INEGI, the Instituto Nacional de Estadística de México, and that gave population per city. Using our cold detailed records, we apply the home detection algorithm that assign a tower, a city to an individual. So we wanted to capture if there is a correlation between the two. And all these points here in blue and red are cities of the area affected, and there the correlation actually is quite nice. That means that the only thing that really means that the distribution of the population of the CDRs and the distribution of the general population is basically the same. Which is a good starting point for these kinds of analysis that you want to measure mobility, right? Okay, so this is a very typical approach to any like big natural disasters. You have a before, something happens, that has a big change in everything, in how you move, in how you interact, and you want to measure how long does it take to get to the original baseline, to get to kind of the before, if you actually get to the before, because that has a lot of economic implications, social implications, and so forth. You want to measure the impact of what happened. So this is the area that was affected. Those are the towers and the people that we identify living in those towers. This is the mobility of a typical week. You see the number of people that move here. This is not actual movement, right? You don't know, this is not GPS, you don't know where they're moving, but you know that at one point they were in this tower and then they moved to this city. Okay, so this is the baseline. This is what actually happened during the weekend, during the week of the floodings. So let me, because I'm running out of time. So the two questions here that we wanted to answer is, first, what the Mexican government wanted to know is, so once an area is evacuated, what was the average distance that individual is evacuated? They really don't have information. There are some specific towns where you can go, but in general, people evacuate yourself, with some exceptions, so they have no information on how far away they go. So 70% of the people were, during the week of the floods, change home less than 10 kilometers. That basically means that you stay in the same urban area. You don't move from your city, you go to a higher ground, or you have another home or friends or whatever, but you stay in your city. In the area of 28% of people is evacuated between 10 and 100 kilometers. This is like a state level, right? You are basically in the state of Tabasco, no neighboring states. That's quite a distance. And 3% of people was evacuated over 100 kilometers. That means you are going somewhere else in the country. Ideally, what you would like to do in this situation is have if possible, obviously, the most amount of people here, because the farther away people are, the longer it takes them to come back. So the longer you take to recover the original baseline. And some people don't even come back. I mean, Hurricane Katrina has a lot of these types of study, and there was a good fraction in the case of Hurricane Katrina of people that didn't come back. In your case, it was less than 1% of the people didn't come back during the period study that we have. And this thing here is the time that it took to people to go back to their home tower. So 67% of people took a week or less. 25% of people took between a week and a month, and over 7% of the population took over 1 month. And actually, I don't think it's here. There was people that even took more than 1 month. This basically states how long does it take to recover your economic activity. You want a lot of people put here. You want people to come back in a week. Obviously, the situation has finished. And for that, you need a lot of people to here. You see, it's very similar. So here you have 70% is in urban area, and you have here 67% that takes 1 week. That's the closer you are, the closer, obviously, you come back. So they're actually, both graphs, although they measure very different things, they are very related. So if you are in the state, it takes you like a month to come back. If you're outside, it takes you over a month to come back. Okay, so I don't think I have time for this, so sorry. let me go over this. I want to just, I want to highlight opportunities and challenges and close with that the presentation, right? So I think big data for social good opens a lot of opportunities. And the first one we need to measure is cost and effort. I think for a best part of companies, the effort is kind of limited. The data is there, it's already been captured, it's being used for someone else. Let's open these new lines. The algorithms are already there. It's just find new case studies. I mean, I think, and this is my particular opinion, that the effort to be put is reduced considering the benefit that you can obtain. Obviously, there are a lot of things to be solved. I was telling you the temporal and spatial granularity. You see the map of a developing economy to compare to a developed economy. How people use the phone has a lot of impact in a country like Spain. 80% of people make or receive more than 2 calls a day. In a country like Mexico, only 20% of the people make or receive more than 2 calls a day. That limits the amount of information that you have. Accuracy has its limitation because of the towers, because of the time, because of just the partial vision you have of the society that you want to characterize. And that opens a lot of challenges. What really put big data social good in general, and in particular for epidemic studies, was Ebola. With Ebola, you had especially these African countries where the level of penetration of cell phones is very big. The main carrier usually is Orange, France Telecom. And everybody was saying, okay, let's give this somebody else CDR because you can trace individuals, you can easily control that. And there was this economist, actually they had it was in the cover how Ebola can be controlled and not being controlled because nobody was providing CDRs. Actually, they cited a H1N1 study in the Economist. And this opened the gate to see, okay, this is useful, we need to use that. Actually, in the end, Orange somehow was given the framework to provide this data set. And this kind of highlighted to public, to everybody that didn't know about it, that the power of using this kind of data for epidemics, for epidemic control. So, obviously you still have a lot of problems. I mean, the main one are internal barriers. Are companies willing to share this information? My answer to that is there's a regulatory thing that you give a company a safe environment. There's no reason why they want to do it. Obviously, there's a lot of regulatory and social limitations. I think whenever when you discuss this kind of study, first thing you do is go to the legal department, they tell you what are the regulations of that particular country and what thing you cannot do. It's one thing from Spain, one thing from Colombia, one thing from Mexico. You can use the data aggregated at this level, and then your studies need to comply with that. It needs to be aggregated, it needs to be encrypted, and so on. But there's not a homogeneous thing. It's a thing that is not really designed for this kind of study. Not only CDR, but if you want Twitter data or Foursquare data, there are studies. Actually, those are not even regulated, right? Regulation only applies to telecommunications, so this kind of internet companies don't really have regulation. So I think we need like a framework that gives us, I mean, you can experiment with humans. There's a protocol that you want to try a drug with a human. There's these protocols that you can follow. But there's not really a protocol. We have an Ebola case in Madrid that was mentioned. I think it will be a fantastic case of let's study what could happen in Madrid with this Ebola case. If something happened and somebody was infected, how can we model the spread of the virus? I have this data that is very powerful to model this thing, and we can maybe even model in real time. But obviously there's no framework for that. That actually in Spain that cannot be done. So we need, I think, a regulation for allowing this kind of studies, one on real time when that's happening, not usually a month or 2 months later when, as usually this particular case, and to give the companies companies and research groups a way of communicating that it's legally and it's covered, right? And I don't think the Ebola case, right, put a lot of institutions on track towards that, and there are a lot of efforts right now, and a lot of some companies, Orange is doing a very good job on that, for example, but there's still a lot of things to be done. In that sense, the most important effort is done by GSMA, which is the Association of All Telecommunications Companies, that is creating basically a data warehouse where everybody puts their data for all the countries they operate. And if something happens, there are some specific companies that can collect the data. That happened, for example, in the Nepal earthquake. Flowminder, which is a company I was presenting before, used that kind of agreement, but still, it's still developing. I think there's a lot of things to be done in that sense. And there are a lot of technical questions that I think they are the least important ones. Technical question is a question of time and money. And you need more, there's a lot of data, you need to put more machines, and it's just a question of wanting to solve that problem. And privacy and security by itself, that's a presentation. I don't need, for me, it's the key element that is, everybody's talking about. The European Union is trying to put something into it, but I think we still have a long way to go to the extent that this kind of studies can be analyzed, for example, in real time. And that will be the power, right? I can study the spread of H1N1 in real time because you have access to the database, because there's a law that the same thing that police can access to CDR datasets in case a judge applies it, that can be done for this kind of situations, and then we can simulate this kind of real time. Okay, so this was all I wanted to present. So there are a lot of papers here. You can access my webpage, and there are the papers there, and this is my email. Feel free to contact me with any questions. The ones I know, I'll answer. If I have to say no, I'll say no. But so I just want to take you of the power of that when you deal with a data set, there's a lot of like standard applications that you can do with big data. Try to move towards something else. Try to move to social good applications. There are millions of applications there that you can do. And that's all. Thank you very much.